My name is Dorna Abdolazimi, and I'm going to talk about the Matroid Partition property and the secretary problem. This is based on a joint work with Karlin, Nathan Klein, and Shayan, Oveis, Gharan. Throughout the talk, assume E is a ground set of elements and W is a non-negative weight function on these elements. Also, let sigma be uniformly random ordering of the elements. So first, I'm going to talk about the secretary problem, which is a special case of the matrix secretary problem. The secretary problem's origin is sort of vague, but by the 50s, it was known by different names to many researchers. So the secretary problem is an online problem in which elements arrive in a random order, and when an element arrives, we learn its weight and must make an irrevocable decision whether to accept it or not. And we can only take accept one element. It is widely known that there is a secretary algorithm A star with competitive ratio 1/e. Which means that for any weight function, the expected weight of the element accepted by a star, where the expectation is taken over the random order, is at least 1/e times the value of the most valuable item. So this ratio is optimal, it's known, but I will use a star to refer to this algorithm in the rest of the talk. Okay. So here I won't talk more about the optimal algorithm and its analysis, but I'm going to go over a very similar algorithm and prove that it has competitive ratio 1/4, at least 1/4. So in the first part of the algorithm, reject the first half of the stream, but keep track of the weight of the most valuable element among them. And in the second half, as new elements arrive, accept the first element whose weight is greater than or equal to the weight of the most valuable element in the first half. So to see why this algorithm has competitive ratio 1/4, consider the weight that consider the event that the second most valuable element comes in the first half, and the most valuable element comes in the second half. And in this case, the algorithm accepts the best element. So the probability of this event is 1/4, and this implies that the competitive ratio is at least 1/4. Now, the optimal algorithm A star is very similar to this algorithm, only in the first part of the algorithm it rejects the first 1/e fraction of the elements, and as opposed to 1/2. So with a more careful analysis, one can show that A star has competitive ratio 1/e, but here the idea is very similar. So the Matroid secretary problem is a generalization of the secretary problem, as I mentioned. And before defining the problem, I briefly talk about Matroids and give some useful examples. A Matroid M is a set function on a ground set E with nice properties that generalizes the notion of linear independence for a finite set of vectors. So we refer to the family of subsets on the ground set E as the independent sets of the Matroid. I won't formally define matroids, but if you don't know the definition, you can think about them in terms of the examples I'm about to mention. So as I mentioned, matroids generalize linear independence. So given any finite set of vectors in the k-dimensional vector space over an arbitrary field F, the family of linearly independent subsets of E forms the independent sets of a matroid called linear matroid. If the vector space is over the field, the finite field with two elements, we call it a binary matroid. And a binary matroid, binary matroids are important to our result, and I will talk about them more and give some examples later. Another useful class of matroids is partition matroids. So given a partitioning of a ground set E, we can define a matroid called a partition matroid with the following independent sets. Any subset of E is independent if and only if it contains at most one element from each part of the partition. And partition matroids are also crucial to our discussion in this talk, and they'll show up a lot. So as an example here, given this partition of the ground set, the first two sets are independent, but the third one is not independent because it has two elements from the last part. Also, throughout the talk, assume that the parts of the partition are indexed in a decreasing order of their sizes, just for simplicity. So, finally, for any graph, we define a matroid called a graphic matroid, and on the set of edges. So the ground set is set of the edges of the matroid of the graph, and independent sets are the set of edges that don't contain any cycle. So I won't explain this, but this is not hard to show that any graphic matroid is a binary matroid. So now we're ready to define, matrix secretary problem. The matrix secretary problem is an online problem introduced in a beautiful and influential paper by Babayov, Imorlika, and Kleinberg in 2007. And in this problem, you're given a matroid in advance, and elements of the ground set arrive in a random order. And when an element arrives, we learn its weight and must make an irrevocable decision whether to accept E or not. So the point of the matroid is that the accepted elements must be an independent set in the matroid. So in the same paper, the authors conjecture that there is a matrix secretary algorithm with constant competitive ratio. Or more precisely, there is a constant C, such that for any matroid, there is a randomized matrix secretary algorithm that for any weight function, the expected value of the elements accepted by the algorithm is at least C times the weight of the best independent set. And the expectation here is taken over the random order and the randomization inside the algorithm. This problem is motivated by applications in online auction theory, but discussing the applications beyond the scope of this talk. Okay, so since this conjecture was introduced, many have worked on this problem, but it still remains open. In the original paper, the authors give an algorithm with competitive ratio omega 1 over log rank, where rank is the size of the maximum independent set of the matroid. And later, others improved this to omega 1 over square root of log rank, and then omega 1 over log rank. There are also various results that achieve constant competitive ratio, but for special classes of matroids, including graphic matroids, transversal matroids, and laminar matroids, and regular matroids. So here's the outline of the rest of the talk. First, I'm going to define the Matroid partition property and the partition reduction-based algorithms. And partition reduction-based algorithms are a class of algorithms that achieve constant competitive ratio for many classes of matroids, including graphic matroids, laminar matroids, transversal matroids. And these algorithms are based on a generalization of the Matroid partition property, which I will define shortly. Given the power of partition reduction-based algorithms, some researchers began asking whether one can design a partition reduction-based algorithm that has a constant competitive ratio for all matroids. And our main contribution in this work is showing that there is no partition reduction-based algorithm that has constant competitive ratio for all matroids. So partition reduction-based algorithms are based on reducing the given matroid to a partition matroid. I will explain more precisely what a reduction means, but before that, it's useful to mention that there is a very simple matroid secretary algorithm for partition matroids that has a constant competitive ratio. Its algorithm is as follows. For any partition matroid P, it is enough to run our optimal classical secretary algorithm A star on each part separately. And, clearly, the set of accepted elements is independent since the algorithm accepts at most one element from each part. And also, the expected value of accepted elements is the sum of expected values of elements accepted by A star in each part. And recall that A star has competitive ratio 1 over E. So the competitive ratio of A P star is also at least 1 over E. So I will say, I will use A P star to refer to this algorithm during the rest of the talk. Okay, now we say a matroid M prime is a reduction of matroid M if its ground set is a subset of the ground set of M, and any of its independent sets is also an independent set in M. For example, here M prime is a reduction of M. One can easily check. So we say matroid M has the alpha partition property for a constant alpha if we can randomly construct a partition matroid P that's a reduction of M, and for all weight functions, the value of the best independent set in P is at least 1 over alpha times the value of the best independent set in M. So if a matroid satisfies alpha partition property, it's easy to design an algorithm with constant competitive ratio for it. It's enough to reduce the matroid to the partition matroid P given by alpha partition property before seeing any of the string, and then run the algorithm AP star on the string. It can be shown that any graphic matroid actually satisfies two partition property, which means that for any graphic matroid based on a graph G, we can randomly construct a partition matroid that's a reduction of graphic matroid, and for all weight functions W, the best value of the independent set in P is at least half of the value of the best spanning forest of the graph G. And then this implies that there's a matrix secretary algorithm with constant competitive ratio for, with like actually 1 over 2E competitive ratio for graphic matroids. So let me give an overview of the proof. Given a partition matrix on, given a graphic matrix on graph G, randomly construct a partition matrix as follows. First, we direct the edges from graph, edges of the graph G to get a directed graph G prime. To do so, with probability 1/2, orient every edge from the vertex with the smaller index towards the vertex with the larger index. But otherwise, orient every edge from the vertex with the larger index to the vertex with the smaller index. Now, let the ith part of the partition be all edges directed towards vertex I in G prime. The first thing one needs to show is that P is a reduction of M, which is equivalent to saying that any independent set in P does not contain any cycle in the graph G. This is not hard to show, and I skipped this part. Second, we need to show that the value of the best independent set in partition matroid is at least 1/2 of the value of the best independent set in M, and or the best spanning forest in G. And let's assume for simply that G is connected, and the analysis is similar if it's disconnected. So consider the optimal independent set in M, which is a tree in G, and let's assume, let's root the tree at an arbitrary vertex, and then direct each edge from the parent toward the child. So for every directed edge ij, with probability 1/2, the direction is the same in the graph G prime. In that case, Pj contains a directed edge ij, and since the other edges incident to J in the directed tree are outgoing edges, no other directed edge from this tree is in Pj. This means that with probability 1/2, the weight of the best element of Pj is at least the value of edge ij, and uniquely corresponds to it also. So in expectation, the value of the best independent set of P is at least half of the value of the tree. Okay, so in their survey of the matrix sector problem, Dennis asked whether all matroids have the alpha partition property for some universal constant alpha. And a corollary of our result, which I will talk about shortly, is that there are matroids that do not satisfy this property. I mentioned that if a matroid satisfies alpha partition property for constant alpha, then there is a matroid secretary algorithm with constant competitive ratio based on a reduction of the given matroid to a partition matroid. But such an algorithm reduces the given matroid to a partition matroid without knowing any of the weights. But one can consider a more general class of algorithms that are based on reductions to partition matroids, and ask, okay, what if we first see the weights of a fraction of the elements and use this knowledge to reduce the matroid to a partition matroid on the rest of the elements, and then run the algorithm for partition matroid on the constructed partition matroid. So more precisely, consider the following set of algorithms. So first, given a matroid M, choose beta between 0 and 1. Then reject the first beta fraction of elements, but based on the weights of these elements, reduce M to a partition matrix P, whose ground set is a subset of the rest of the elements. Okay, I'll call this set of all elements on E that are not in the partition matrix R. So here's an image. Then having a partition matrix P, run AP star on the rest of the string. In addition to graphic matroids, which we discussed before, there are partition reduction-based algorithms for transversal matroids and laminar matroids that have constant competitive ratio. And as opposed to the reduction for graphic matroids, these reductions are constructed after seeing the weights of a fraction of the elements. So it wasn't, because this class of algorithms have a great performance on various classes of matroids, and people wondered whether there is a reduction-based algorithm with constant competitive ratio for all matroids. And our main theorem is that there is no partition reduction-based algorithm that achieves constant competitive ratio on binary matroids, which I defined shortly, but this main theorem suggests that for resolving matrix secretary conjecture affirmatively, one needs to look for algorithms outside this class. Okay, let me first define the complete binary matroid. The complete binary matroid, BD, is a binary matroid on all elements of the k-dimensional vector space on the finite field with 2 elements. So the size of the ground set is 2 to the d minus 1. And recall the independent sets of this matroid are all sets of vectors that are linearly independent. So here you can see all the elements of B3, and below there are 2 examples of the independent sets. And the third set, however, is not independent because the sum of these 3 vectors is 0. So we derive our main theorem, which I mentioned earlier, from another theorem, and this other theorem is written above. So roughly speaking, this theorem says that for any reduction of BD to a partition matroid P with all with parts P1 to PD, almost all elements of P are concentrated in very few parts. So more precisely, excluding the larger order of square root D parts of the partition, all other parts combined contain only D to the minus 1 over 4 fraction of the elements of the binary matroid. So our main theorem is a corollary of this theorem. And, to state our main theorem more precisely, again, this we prove that given a D that is large enough, any reduction-based algorithm that has competitive ratio at most D to the minus 1 over 4. And, first I want to explain on high level how we derive the corollary, which is our main theorem, from the above theorem. Okay, so the proof idea is as follows. First, sample D elements from the ground set of BD uniformly at random with group placement. And then let the weight of these elements be 1 and the weight of the rest of the elements be 0. So it's not hard to see that the expectation of the best independent set has at least D over too many elements with weight 1. On the other hand, for any partition matroid, the optimal independent set has at most order of D to the 3/4 many elements with weight 1. It's like too little. So to see this, we use the above theorem. Since the elements with weight 1 are distributed uniformly, the above theorem implies that most of these elements are concentrated in in order of square root D largest part of the partition. And any independent set of this partition matrix can only take one element from each of these large parts, so the gain from them would be at most square root D. And in the rest of the parts, in expectation, there will be at most order of D to the 3/4 many elements with weight 1 all combined. So the gain from these parts is at most order of D to the 3/4, which gives us what we wanted. It's just a proof idea. So let's assume this is proved. Now it remains to prove this theorem. So then a reminder, when BD is reduced to P, by definition of reduction, the ground set of P is a subset of M. So the elements of M might fall outside. Some of the elements of M might fall outside of P. And I denote the rest of the elements of BD that are not in P by R. So how do we prove this theorem? So we prove this theorem by an inductive application of a lemma that says that the largest part of the partition is very large. And just inductively, we prove this theorem. So the proof of this part is, this induction gives a theorem is not hard, and I won't talk about it. But an important point to mention is that allowing P to not contain all elements of the binary matrix is a fundamental point about this lemma. Since without allowing this by induction, the induction would not go through. So here I want to mention two related papers. In independent work from ours, Lichter, mostly in prose, showed that for any constant B, the matroid BD is little o of square root D indecomposable. I won't explain what this means, but for B equal to 1, this implies that for any partition matrix that is a reduction of BD and contains all elements of BD, or equivalently assuming R is the empty set, the largest part of the partition has at least omega 1 over square root D fraction of the elements. In a subsequent work, Van der Poel shows a similar result, which, it implies that for after setting B equal to 1, implies that for any partition matrix that is a reduction of BD and contains a random subset of the elements of BD, or equivalently assuming that R is a random subset, the largest part of the partition has little omega of 1 over D fraction of elements with high probability. And these, as you can see, these results are neither stronger or weaker than the lemma written above. To the best of my knowledge, because of these assumptions on R that these results have, then they cannot be applied inductively to get the above theorem. In the rest of the talk, I want to focus on this lemma, but in this talk, to demonstrate the main idea of the proof, I proved the lemma with the extra assumption that P includes all elements of M, or equivalently, R is empty. So I proved this simplified version. So I start with a simple fact. Given partition matroid that is a reduction of BD, for any elements X and Y that are in different parts I and J, the sum of the elements is either in part I or in part J. So why? The proof is very simple, but since the set X, Y, and X plus Y is a dependent set, they can't be in three different parts of the partition. So, the fact follows. So we're ready to prove the lemma in the simplified form. And in the proof, let n be the number of elements that is 2 to the d minus 1. So the proof follows from a double counting argument. Assume a contradiction that the size of P1 is less than n over 8. Okay, and considering graph on the elements whose edges are pairs of elements that are in different parts. Okay, so here I have partially specified the partition on elements of B4, and they're on the edges based on these partitions. So for instance, like there is no edge between 1 and 2 because they're in the same part P2. Now, first, let's lower bound the number of edges. The number of edges in the is the total number of pairs of elements in the matroid, which is n choose 2, and the number of pairs of elements that are minus the number of pairs of the elements that are in the same part of the part of the partition. So considering the assumption we made by contradiction, the second term is maximized when there are 8 parts of size n over 8, and the rest of the parts are empty. It's not hard to see. Using this fact, we can upper bound this term by n squared over 8. It follows the number of edges can be bounded below by n squared over 4. Now, we find an upper bound on the number of edges. For this purpose, make the graph directed as follows. So recall that for every edge, x and y, where x is in part I and y is in part j, if the sum is in part, that the sum is either in part I or in part j, and if the sum is in part j, direct the edge towards y, and otherwise direct toward x. So in this example, I'm showing the direction of one of the edges. So say the edge between 2 and 3. And the sum of the elements 2 and 3 is element 1, which is in part 2. And element 2 is in part 2 as well. So the direction is from 3 to 2. Now consider an arbitrary vertex x of the graph that is, say, in part I. And consider two arbitrary incoming edges yx and y prime x. So x plus y and x plus y prime are have to be two distinct elements in Pi. So any edge directed towards x corresponds to a unique element in Pi, and therefore the degree of x is at most the size of Pi, which is n over 8 by our assumption. And this gives an upper bound on the size of the number of edges, which is n squared over 8, and clearly this contradicts the lower bound we derived earlier. Okay, to summarize, applying this lemma, we can prove this theorem that says that for any reduction of complete binary matroid to a partition matroid, almost all elements of the partition are concentrated in very few parts. And a corollary of this theorem is our main theorem that says no partition-based algorithm, partition reduction-based algorithm has a constant competitive ratio for complete binary matroids. Finally, here are some open problems beside the obvious open problem, that is the matrix secretary conjecture in its general form. I think our work confirms that graphic matroids do not really capture the behavior of general binary matroids with respect to this problem. And the binary matroids are hard instances, so one might want to focus on binary matroids and try to find out whether there is a matrix secretary algorithm with constant competitive ratio for binary matroids. Second, more vague question to consider is that can we use reductions to other classes of matroids to design a matrix secretary algorithm with constant competitive ratio for all matroids? Thank you.